Now, having seen Pascal's triangle and some of the important properties of Pascal's triangle, I want to talk about binomial expansions. You might not have seen that term before, but you've already computed those many times when you were young, learning how to expand expressions in algebra. A binomial expression is just an expression that's a sum of two things. Those can be anything, so we'll call them A and B. You have a sum of A plus B and you want to raise it to some power. Whenever you want to raise a sum of two things to some power, that's a binomial expansion. Or when you want to expand such an expression, that's a binomial expansion. And so here are some simple examples of binomial expansions. You want to raise the sum A plus B to the 0th power, that's just going to be 1. Trivial. You want to raise the sum A plus B to the 1st power, that's just A plus B. Again, that's trivial. You want to raise the sum to the 2nd power, you all are totally comfortable with this, I'm sure. That's just A squared plus 2AB plus B squared. You learned that in middle school or maybe in early high school. You should all be comfortable with that. I'm sure all of you have tried at some point, maybe you've forgotten it, but what happens when you cube the quantity A plus B? You end up with A cubed plus 3A squared B plus 3AB squared plus B cubed. Now, if you don't have that memorized at the tip of your tongue already, it'll be easy for you to remember that shortly. But if you haven't done that in the past recently and didn't have that memorized, you could always figure it out by multiplying this previous one, A squared plus 2AB plus B squared, by the quantity A plus B. You can pause the video, spend a few seconds, expand it out, and you'll see that this is correct. But now you should be recognizing something here. Here we have, if we look at just the coefficients, we have a 1 first, which is trivial. The coefficients are 1 times A and 1 times B. So we have, I'll write just the coefficients, 1, 1, 1, 1 times A squared plus 2 times AB plus 1 times B squared. Then we have coefficients 1, 3, 3, 1. And you might be guessing something's going on here. This looks very much like Pascal's triangle. Can you guess, if you haven't seen this before, what A plus B all to the 4th power is? Well, the coefficients you can guess would be the next row of Pascal's triangle, 1, 4, 6, 4, 1. But what would the other parts be? Notice that when you square A plus B, every term has power 2. You have an A squared, you have a B squared, and here you have a mixed term with 1A and 1B, so the total power is 2. That's true in every case. A plus B to the nth power, this total power of any term will be n. So you would guess that everything here will, in A plus B to the 4th power, will have a total power of 4. And here I've just listed them in decreasing order of the power of the A term. So we could write that as 1 times A to the 4th. The next thing you might think, is 4 times A cubed times B, 3 A's and 1 B. Then you might have 2 A's and 2 B's. Then you might have 1 A and 3 B's, 4 AB cubed. And then you have 1 times B to the 4th. And that turns out to be exactly right. And this pattern, I claim, continues. And that's an amazing thing. It's called the binomial theorem. Now, how could we demonstrate that the pattern continues? Well, I claim that as we go from A plus B to the 4th to the next one, A plus B to the 5th, it's a very natural thing that the coefficient of the term, and here I'll just write a single term, and I'll hope to convince you by doing so that this works everywhere. If I just want to look at a single term, say A cubed B squared. Here's one of the terms that has a total power of 5, the one with 3 A's and 2 B's. You might ask, how do I get a term that looks like A cubed B squared when I multiply A plus B times A plus B all to the 4th power? And this, of course, is that previous row. Well, if I take that previous row and multiply by A plus B, it's like multiplying by A and adding what you get when you multiply by b. In other words, we take the stuff above it and we multiply it by a, and we multiply it by b. Well, when I multiply this 6a squared b squared by a, I'll get 6a cubed b squared, because I'm taking a times this. Now when I multiply the other ones by a, I'll get other stuff, but it won't look like a cubed b squared. So I'm just not going to write it down now. But a times this previous line here will include a term that looks like 6a cubed b squared. But it will also, I'll also get a contribution from multiplying b by the previous line. And when I multiply this term here by b, the 4a cubed b, and multiply it by b, I get an a cubed b squared, and I get 4 of those. When I add those together, I get a total of 10 a cubed b squared. And that would be exactly the term beneath and in between those when I write out this expansion. I'll show you one more term here. How many a squared b cubed terms did I get? Well, when I multiply this by b and when I multiply this by a, I get a squared b cubed terms, so I'm going to total of 6 plus 4, which is 10 of those. And we'll just finish this out, or not quite finish. If I want to have an a b to the 4th term, I could take b times this term plus a times this term, and again I'll get the 4 plus 1, which is 5 of those. It should be easy to see. I'll get a single b to the 5th term, and I'll leave you to fill in these. You'll start with a to the 5th, and you'll get 5 a to the 4th b. And you see, just by the rules for multiplication, these algebraic rules for multiplying by a plus b, the coefficient of the correct term is just the sum of the two coefficients above. In other words, the pattern for Pascal's triangle is followed exactly for binomial expansions. And since the binomial expansions start with the coefficients from Pascal's triangle, and the pattern continues for both binomial expansions and Pascal's triangle in exactly the same, I should say with exactly the same recursive rule, we know that that pattern continues. How can we state this binomial theorem in a simple, formal manner? Well, if we just look at the nth term, I should write it here, a plus b to the nth power will look like the coefficients from the nth row of Pascal's triangle, n choose 0. You'll have the a to the nth plus n choose 1, a to the n minus 1 b, plus n choose 2, a to the n minus 2 b squared. And we're going to keep going all the way up to the very last term, which is n choose n b to the n. And we can write that more compactly using this sigma notation, the summation notation. Just let this lower entry be what we call k. It will go from 0 at the beginning all the way up to n. So we're going to sum up from k equals 0 to n choose k. Here we'll have a to the n minus k, and multiplying by b to the k. So this is a beautiful theorem. It's the binomial theorem. It works for any expressions a and b. A common use of the binomial theorem when you're talking about interesting functions is to let a be 1 and b be x, and then the same thing, say when n equals 5, is just an expansion of 1 plus x all to the 5th power is 1, that's the 1 to the 5th, plus 5x, that's 5 times 1 to the 4th times x. Then you have 10, that's the next entry in Pascal's triangle there in row 5, times 1 cubed times x squared. Again, you'll have 10x cubed, 5x to the 4th, and 1 times x to the 5th. These coefficients come from the 5th row of Pascal's triangle, and the powers of x will just be increasing. In fact, you can, in general, write 1 plus x all raised to the nth power as 1 plus nx plus n times n minus 1 over 2 times x squared, etc. And I'm writing it this way. This is what you might see when you're studying functions, but you can recognize that 1 as n choose 0, that n there as n choose 1, n times n minus 1 over 2, which you could also write as n times n minus 1 over 2 factorial, is n choose 2, that's this part. This is just n choose 3, n times n minus 1 times n minus 2 over 3 factorial, and it keeps going all the way up here. You'll have n choose n minus 1, which is just n, and here the coefficient of 1 is just n choose n. So this is how you can expand an expression like 1 plus x to the nth power. Here's some more examples. What if you let A be 1 and B be 1? Well, then you get 1 plus 1 to the nth power is, and choose 0, times 1 to the nth, I'll write it here, 1 to the nth times this 1 to the 0th power, plus n choose 1. Then you'll have a 1 to the n minus first times 1, and it's still going to be 1 to the nth, or just 1. These terms will always be 1, so I'm going to stop writing them. You'll have n choose 2, n choose 3, all the way up to n choose n minus 1, plus n choose n. These are, of course, always 1. So this is just the sum of the entries in row n of Pascal's triangle. And what number is this sum? Well, of course, that's a triviality on the left here. 1 plus 1 to the nth power is what we call 2 to the nth. 1 plus 1 is 2. So this tells you that the sum in the nth row of Pascal's triangle is precisely 2 to the nth power, using the binomial theorem. I believe this question comes up in the book. Try to make an argument that doesn't involve the binomial theorem at all for why this should be true, that the sum of the entries in the nth row should be 2 to the nth. Now, we've already seen this, of course. We've already seen, using a combinatorial argument, that this sum n choose 0 plus n choose 1 all the way up to n choose n is 2 to the nth. We made a combinatorial argument for that. See if you can find another argument, different from any of the ones we've had so far, to show this. It's really useful when you know something's true, not just to say you know it's true and then ignore it, but to find more ways that you can understand why it's true. Not just one way, but lots of ways. Here's something else that's fascinating. What happens if I put here a equals 1 and b equals minus 1? So that we'll have a plus b is 1 minus 1, and we raise it to the nth power. Well, that will be n choose 0, and we'll have that times 1 to the n. Then we'll have n choose 1, and we'll have 1 to the n minus 1 times minus 1. And here, I'm going to put minus here. I'm going to cross this out. That's just 1. Let me actually erase this and try to make this a little bit nicer. N choose 0 will be multiplied by 1 to the n. N choose 1 will be multiplied by 1 to the n minus 1 times a negative 1, so we'll have a minus here. N choose 2 will be multiplied by 1 to the n minus 2 power, and then negative 1 raised to the second power, which is now positive, so we'll get a plus there. Then we'll get a minus n choose 3. You'll end up with a plus n choose 4, and it'll keep going like that through the nth row of Pascal's triangle. The last term I'll write is plus or minus n choose n, which is just the 1 there. I say plus or minus because if n is odd, that'll be a minus sign that you end with. If n is even, you'll end with a plus sign. But what do you get when you do this? This is what we call an alternating sum of row n of Pascal's triangle. We add up the terms and we alternate positive and negative. The claim is you get this quantity 1 minus 1 to the nth power, but that's always 0 because that's 0 to the nth power. So the claim is when you look at Pascal's triangle and you do an alternating sum, you always end up with 0. Now let me go back here to where we wrote our biggest form of Pascal's triangle. Here's our biggest one, Pascal's triangle. Look at some of these. If you look at row 5, you might say that's obvious that an alternating sum will give you 0 because I'll have 1 minus 5 plus 10 minus 10 plus 5 minus 1. Well, this 1 will cancel a minus 1. This 5 will cancel a minus, the minus 5 will cancel a 5. This plus 10 will cancel a minus 10 when you do an alternating sum. There's symmetry in Pascal's triangle, which is caused by this fact that n choose k is the same as n choose n minus k. So for odd rows, it should be kind of obvious that the alternating sum is 0. But look at an even row like row 6 here. The alternating sum would be 1 minus 6 plus 15 minus 20, again plus 15 minus 6 plus 1. It's not obvious that these all cancel out because you're adding the two 15s together, you're subtracting the 20 and both 6s, and you're adding both of the 1s. Well, in your head, try to add these up, or I'll just run through that with you. You're getting a positive 15 plus 15 is 30, plus 2 1s is 32. You're getting a negative 20 and 2 minus 6s, so you're minus 32. That ends up being 0. And it is not at all obvious that an alternating sum, especially here when you're talking about even rows of Pascal's triangle, always add to 0. But they do, and the binomial theorem guarantees us that. That's down here. This is our result for that. I think this is problem 14 there in the book. That one's not one I asked you guys to do because I wanted to talk to you about it right here. But it's an amazing fact. It'll be useful for us later, so don't forget this fact. You can get all sorts of interesting results with the binomial theorem. What happens when you expand 1 plus 2 to the nth power? Well, you get n choose 0, which is 1. You'll get n choose 1. I'll just leave it as n choose 1, but you could write that as n. Times you'll have 1 to the n minus 1 times 2, so you'll have 2 there. The next term will be n choose 2. And you'll have 1 to the n minus 2 power, but 2 will be squared, so you'll have 2 squared. The next one will be n choose 3 times 2 cubed. And it'll keep going like this, 2 to the 4th, n choose 4, plus 2 to the 5th, n choose 5, all the way up to 2 to the nth times n choose n. Of course, n choose n is just 1. And what happens when you add all these binomial coefficients, each multiplied by the appropriate power of 2? Well, you get 1 plus 2 to the nth power, which is 3 to the nth power. So you can take a power of 3 and split it up in this amazing way. It's just a really neat formula that one can prove true very easily using the binomial theorem. I hope you'll spend some time looking at all sorts of other things you can do with Pascal's triangle, and we'll talk about some more maybe in our discussion sections.